So we're taking a look at section 4.2 still, but we're looking at what's called area under a curve, and this is going to show you what we use that summation stuff that we learned in class for. This is kind of a challenging lesson, so make sure you take good notes and pause the video as needed. So make sure you have these summation formulas in front of you. They should be in your notes from class, but make sure you have them nearby because you're going to want to refer to them as we go through this lesson. You don't have to memorize these formulas. By the way, I know I make you memorize a lot of stuff in this class. This is something I'll provide you on a test if you need it, but just make sure you have them handy and you know how to use them. So can you think of a way that we could approximate the area under this curve? Let me back up for a second. In calculus, there's two sort of big challenging questions that mathematicians wanted to have answers to, and one of those was to find the slope of a function at a different point, which meant to find the slope of its tangent line, and that involved the derivative. So the other sort of big challenging question that mathematicians needed to figure out was how to find the area under a curve when it's not a straightforward shape that we're familiar with, like a circle or a triangle or a square or a rectangle or something like that. And so other functions where the area changes depending on what part of the graph you're looking at. In other words, like the area down here from 0 to 1 is going to be a lot narrower and not consistent. It's not going to be consistent, but it's going to be narrower than, say, area further out because we've got a function that's changing the entire time. And that's where calculus comes in. So if we could think about how we could approximate this area, what mathematicians historically started doing was they said, all right, let's subdivide this into rectangles because we know how to calculate the area of a rectangle. So there's this, if we're looking at this, say, from 0 to 4, the most natural way I think would be to subdivide it into 4 rectangles of equal width. So the width of each rectangle would be 1. The height varies depending on where you're at on the curve, right? So like the height at 3, for example, is going to be a different height than the height, say, at x equals 0. The width, however, is the same. I've subdivided it so the widths are the same. The height is f of x sub I, I'm calling it. So in other words, the y value, right? The y value, depending on where you're at a particular x value. So the first rectangle would be 1 is the width times the height, which is f of 0. Now I can see that that's 1 from looking at the graph, but it would be at the value of the function where x is 0. The next rectangle would be a width of 1 times f of 1. The next rectangle would be a width of 1 times f of 2, so the height where x is 2. The next rectangle would be 1 times f of 3, so the height where x would be 3. I do want to say also this is really kind of a poorly drawn figure. F of 3, for example, if you plug that into the function, that would be 3 squared. So 9 plus 1 would be, which would be 10. This is certainly not at a y value of 10, so don't let that throw you. Think about it algebraically, though. What is f of 1? What is f of 2? What is f of 3 for this particular function? So if I substitute those values in, I get 1 for the first height, 2, 5, and 10. And then we crunch those numbers, we get an approximation of 18. Now, how good is this approximation? Well, I mean, it certainly under approximates it because you can see there's some space that we're not including under the graph. But it's an okay approximation. How could we make this a little bit better? Well, that's what mathematicians struggled with. They said, okay, how can we make this better? Well, what if we subdivide this into more rectangles? Does that get us a better approximation? By the way, this is called a lower sum. You're going to see that term in the book. This is called a lower sum. The reason it's called a lower sum is because it under approximates the area. If we drew the rectangles differently so that it over approximated the area, we would call that an upper sum. So let's look at that picture. So the same function, I'm going to draw the same 4 rectangles, but this time notice where I'm drawing them. At each interval, I'm drawing them at the right endpoint instead of at the left endpoint. Let me go back to that previous picture. I want you to see that. In the previous picture, I drew the rectangles at the left endpoint of each interval. So between 0 and 1, I drew the rectangle height at 0. Between 1 and 2, I drew the rectangle height at 1. Between 2 and 3, I drew the rectangle height at 2. And that gave me a lower sum because it was an under approximation. In this picture, I'm drawing them at the right endpoints. And that's creating what's called an upper sum because you see it's over approximating the graph. But the way we would calculate the approximation, or that we'd approximate the area, is the same idea. So we've got 1 times this time the height is f of 1 for the first rectangle, plus a width of 1 times f of 2, plus a width of 1 times f of 3, plus a width of 1 now times f of 4. So again, if we calculated those numbers by getting those values for y from the function x squared plus 1, we get an approximation of 34. And like I said, this is called an upper sum because it over approximates the area. How good is this? Well, we had 18 for our under approximation or our lower sum. We have 34 for our upper sum. It's a pretty big range, right? So we know the area is somewhere between those two. You know, there's different things we could do. Maybe we could average them together and get an approximation that way. But the most natural way that mathematicians came up with that they thought worked was to subdivide these into smaller intervals, okay? Think about what happens. I've subdivided this into 4 intervals by making them all have a width of 1. But if I subdivided them so they had a width of 1/2, then I would have 8 rectangles, and so forth. If I subdivided them so they had a width of 1/4, I'd have more rectangles. And I could subdivide this into smaller and smaller widths, which would give me more and more rectangles. I want to take a little aside here from the PowerPoint and show you a demonstration in Desmos. So this is the same function, x squared plus 1, that we were just taking a look at. And what we're looking at is the area under the curve from 0, so a is 0, that's the left endpoint, to b equals 4, that's the right endpoint, from 0 to 4. So if I approximate it with 4 rectangles, it gives me, so right now it's doing a left-handed or an under approximation or a lower sum with 4 rectangles. These are the 4 rectangles I had, a little bit more accurately drawn, but these are the same 4 rectangles I started with in the PowerPoint. Remember, that gave me a sum of 18. So what I want you to notice is, as I increase the number of rectangles, so right now I'm at n equals 4, as I increase the number of rectangles, what happens to these gaps in the graph? What happens to the area under the curve? So there's 7 rectangles, there's 9, there's 11, there's 12. Do you see that we're lowering that gap between the areas that the rectangles are approximating and the area under the curve? So that gap is getting smaller. Now I'm at 16 rectangles. The more and more rectangles I add, the better my approximation. Do you see that? Now I'm up to 33 rectangles, 37. Now I'm a little limited by the pixel technology here. Let me zoom out a little bit, or zoom in rather. So let's see if that does anything. So you can't see the entire graph here because of the way I'm zoomed in. So now I'm looking at just this part here. But now I'm up to 38 rectangles, and you see that they're filling in and approximating that area under the curve better the more rectangles I add. Now this Desmos application will only let me go up to 100. That's as far as it'll let me go. You can see even at 100, there's still a little bit of a gap. I wonder if I can zoom in a little more. You can still kind of see there's a little bit of a gap. But the idea is the more rectangles I add, the better my approximation is. And hopefully this makes you think of the idea of a limit, right? That's what a limit is. If we take the limit as the number of rectangles goes to infinity, theoretically we should get the exact area under the curve. And that's what we're going to do. So let me go back to the PowerPoint here, and let's take a look at that. So I'm going to give you a different function. We're going to look at f of x equals x squared, and this time we're only going to go from 0 to 2. So I'm going to partition this into n subintervals of equal width. So think about this. If my entire interval goes from 0 to 2, would you agree then that the width of each rectangle would be b minus a over n? So in my example, 2 minus 0 divided by n. Do not overthink this. 2 minus 0 is the entire interval. If I divide it by the number of rectangles I have, that would be the width of each rectangle. So my width is 2 over n. Okay? As n goes to infinity, the number of rectangles, as that increases, we get a more and more accurate approximation, just like we saw in Desmos. What are the corresponding x values for each partition? So if we start at the left endpoint, x naught, we'll call it, would be 0. If we add a width of 2 over n, the next interval, or the next x value, would be 0 plus 2 over n, the distance I've traveled to get to through the width of the next rectangle. And I'll be honest, you don't have to write all of these little things down for this problem. If you just want to sit back and relax for a second, I'll summarize these steps on the next slide. But just watch and kind of see if you can follow along with what I'm doing. The next x value, we'll call it x sub 2, would be 0 that I started with plus 2 of the rectangle widths. And then the next one would be 0 plus 3 of the rectangle widths. So the ith rectangle, or the ith, it sounds kind of funny to say, I know, the ith x coordinate would be 0 plus I times the width of a rectangle, or just 2I over n. So any x value can be approximated by 2I over n. Okay? And then the last one would get me to 2. All right, so where are we going to go from here? Well, what do we want to do? We want to get the area of each of these rectangles. And then once we get those areas, we want to add them all together. So the area of one rectangle, if the width was 2 over n, so remember the area of a rectangle, it's the width times the height. Well, the width was 2 over n. The height would be the y value that corresponds to each x value, which I just defined as 2i over n. So it'd be f of x sub I, which would be 2 over n times 2i over n squared. Where am I getting that from? Remember what the function was. The function was y equals x squared, right? F of x equals x squared. So to get the corresponding y values, I'm going to plug in that 2i over n in place of the x. So that gives me 2i over n squared because the function was x squared. So we want to get the total area, which means we want to add all those rectangles together. Hopefully you remember the lesson we talked about in class today, which was on summation. So we're going to sum all of those together. So we're going to do the sigma of the area of each rectangle. So 2 over n times 2i over n squared from 1 to n. Now, in a little algebra here, that simplifies to 8i squared over n cubed. What do we want to do with n? We want to take this approximation to get it really good. We want to take n to infinity. So that means we're looking at the limit as n goes to infinity of that summation. And that ties back to the summation formulas we talked about earlier. So to find this limit, we're going to simplify the summation by first taking out 8 over n cubed, because that is a constant. I squared, we have a formula for that. The formula, look back at your notes, for the sigma of I squared. Even if you're a little confused right now, hopefully you can catch up with me by looking at your notes and looking at the formula for the summation of I squared. That's in your notes. So what's that formula? That's n times n plus 1 times 2n plus 1 all over 6. Do you see that in your notes? Times the 8 over n cubed that was in front. If we clean this up, do a little algebra, simplify this a little bit, we're taking the limit as n goes to infinity of this expression. You notice that the degree of the numerator and the degree of the denominator are the same, which means we look at the ratio of the leading coefficients. So that would be 16 over 6, 8 times 2, 16 over 6, which reduces to 8/3. 8/3 is the true area under the curve for this function from 0 to 2. Now, let's summarize this process. So if you stopped writing notes for a second, go ahead and write these 5 steps down, because these are 5 steps we're going to follow whenever we do these. Okay? Step 1. Well, let me back up. First thing you're going to do is you're going to draw a picture. So always draw a picture. Write that down. Always draw a picture. Then step 1 is you're going to find the width of each rectangle. So the width of each rectangle is always going to be b minus a over n every single time. Step 2, you're going to find a representation for each x coordinate. That was that x sub I that I wrote down. So x sub I is always going to be a, whatever the left end point is. If we're lucky, it's 0, but it doesn't have to be. A plus I times your width, b minus a over n. We're going to write the representation for the area of one rectangle. How do you get the area of a rectangle? It's the width times the height. Well, the width is the b minus a over n. The height is f of x sub I. So whatever your x sub I expression is from step 2, you're going to plug it into the function to get f of x sub I. So that's going to depend on what the function is. You're going to write a summation for all of these. So you're just going to stick a sigma in front of that expression you just came up with in step 3. And then last step is you're going to take the limit. So you're going to find the limit of that summation that you wrote in step 4 as n goes to infinity. The hardest part of this is the algebra. I think you all can handle the calculus. It's not even really a lot of calculus. The limit's the only calculus we're applying. It's the algebra and getting everything set up. So let's take our time and let's do one. So let's find the area under the curve, y equals 2x plus 2, and they want us to go, it looks like, from -1 to, let's see, 1, 2, 3, 4. All right, so find the area, I'm sorry, not -1. They want us to go from 0 to 4. That's part of the directions. Usually they'll tell you what interval to go from. So in this case, they gave us the area under the curve, 2x plus 2, but they want us to range from 0 to 4. All right, so the width would be b minus a over n, so that's 4 minus 0 over n, which is just 4 over n. X sub I is going to be a, which was 0, plus I times the width. So that's I times 4 over n, which is 4i over n. What was step 3? Step 3 was to write the area of one rectangle. So that would be the width, 4 over n, times f of x sub I. Now, how do I get f of x sub I? I'm going to take this 4i over n, and I'm going to plug it in to the original function in place of the x. So in my example, that's 2 times 4i over n plus 2, because the function was 2x plus 2. We're going to write this as a summation, and I went ahead and added the limit in the same step, so I combined steps 4 and 5. Just for time's sake, trust me on the algebra here. This crazy algebraic expression simplifies to this expression right here, 32i over n squared plus 8 over n. We can separate this into separate summations. Remember, you can always separate sigmas if that helps. So I'm going to separate them, and I'm going to take the limits with each one. 32 over n squared, of course, is a constant, so I'm going to move that to the front of the sigma, so that first sigma just leaves me with I. 8 over n is also a constant, so that leaves me with just 1, because there's nothing else in this expression right here. Now look back at your summation formulas. What is the formula for just I? That was 32 over, that was n times n plus 1 over 2 times the 32 over n squared that was in front. 1, the summation for 1, that's a constant, so it'd be 1n, which is just n. So we have 8 over n times n. Clean that up a little bit. Take the limit of each expression. The degree of the numerator and denominator are the same for the first expressions. That becomes 16 plus 8, so that gives me 24 for my final answer. Now, this you may or may not have noticed. This was a trapezoid, right? This is a trapezoid region, so we could have calculated this using geometry. You may not remember the area of a trapezoid, and that's okay. I'm just going to tell you what it is. It's 1/2 base 1 plus base 2 times the height. In this case, the base is 2, base 1 is 2, base 2 is 10. The height is the distance between them. The bases are the sides that are parallel. That's 4, so the area is 24. And that's what we got using our summation, was 24. So the method does work. We just proved it using geometry. Let's try another one. Find the area of the function f of x equals x cubed, bounded by the x-axis, and from x equals 0 to x equals 1. So I've got a picture of it. I want to go, this actually goes through the origin, this function. It's a little hard to tell from this picture, but it goes through the origin. So I want to go from 0 to 1. Now notice I can't use geometry on this because it's a cubic function. It's not a straight line like it was in that last picture, so I have to use this method. So let's start with the width. So the width of each rectangle, remember, is b minus a over n. So that would be 1 minus 0 over n, or just 1 over n. X sub I, step 2, would be a plus b minus a over n times I. So in my example, a, of course, is 0. That's the left endpoint. b minus a over n is the width, so 1 over n times I becomes just I over n. Area of one rectangle, so that would be the width, 1 over n, times f of x sub I, which is I over n. Well, how do I get f of x sub I? So that means I'm going to take this I over n, I'm going to plug it in to the function where the x is. I'm going to replace the x with I over n, so that gives me I over n cubed. We're going to put this into, cleaned it up a little bit, I cubed over n to the 4th is that new expression. We're going to put that into our sigma formula, and I went ahead and combined step 4 and 5 and put the limit in front of it. Step 5 is just adding the limit, but you're going to put it in your sigma. So we have I cubed over n to the 4th. Now I'm going to treat n's, remember, like a constant. So I'm going to move the 1 over n to the 4th in the front, because that n to the 4th is in the denominator, so that's 1 over n to the 4th. That leaves me with I cubed. Look back at your notes. Like I said, even if you're a little fuzzy, you can do this part. Look back at your notes. What's the formula for the sigma of I cubed? you should be giving me n squared times n plus 1 squared all over 4. Now we can take the limit of this. Once we've replaced the sigma with its correct formula, we can take the limit as n goes to infinity. These have the same degree because if you FOILed this out, you would get n to the 4th as the leading coefficient, or as the leading term. The coefficient would be 1, so since they have the same degree, we get 1/4 as the limit, and that would be the area under this curve from 0 to 4, or 0 to 1. Let's try one more. Find the area bounded by the function f of x equals 4 minus x squared, the x-axis, and x equals 1 to x equals 2. So let's be clear what we're talking about. So it's bounded by the parabola 4 minus x squared. We want it to go from x equals 1 to x equals 2 and bounded by the x-axis. We don't go below the x-axis. I want to be clear on that. We're talking about closed bounded regions. So we're looking at this little wedge right in here from x equals 1 to x equals 2, but it stops at the x-axis. So let's go through our steps. Step 1 is to get the width. So look back at your notes. B minus a over n, you can do that part. So b minus a over n is 2 minus 1 over n, which gives us 1 over n for the width. Now what is x sub I? X sub I is a plus, look at your steps that you wrote down, a plus I times the width. Well, a this time is not 0, it's 1. So it's going to be 1 plus I times the width, 1 over n. So 1 plus I over n if we simplify that. We want the area of one rectangle. I'm on step 3. So the area of one rectangle is the width, 1 over n, times f of x sub I, so your expression from step 2, f of 1 plus I over n. Now here's where the algebra gets a little tricky when we don't start it at 0. Let me show you what's going on. 1 plus I over n, we're going to plug that in to x in the original function. Well, the function was 4 minus x squared. So 4 minus x squared becomes 4 minus 1 plus I over n squared. That's the x sub I expression. Now, I'm going to forgo the details here, but what we would have to do is we'd have to FOIL this out. We'll do some more practice with this in class tomorrow, so we'll go through the algebra together. But what we would do is we would FOIL this expression out and combine like terms. And then distribute the 1 over n. That gives me this expression. We're going to put that into our summation. Whoops, let me go back. Don't take the time and do the algebra. Just trust me on the algebra for right now. I want you to focus on the steps. That's the main thing right now. Do you see what I did? I took this expression, I simplified it algebraically, I got this expression, I'm putting it into my sigma, and I'm putting the limit in the front. Now remember these sigmas, we can separate them, so it might be beneficial to look at these as 3 separate summations. And there they are. Notice let me go back, notice the 3 over n in the front, I wrote that as 1 over n times 3 minus 2 over n squared. I like to take the n's out front and treat those as a constant because I think it makes it easier to see the summation formula on the inside of the sigma. I left an I there, and then I just have an I squared in the last one because I took 1 over n cubed to the front. Now, go ahead and replace these. Pause the video. Replace each of these summations with the appropriate formula in terms of n. The first one, the 3, became 3n. The second one, the I, became n times n plus 1 over 2. The last one, I squared, became n times n plus 1 times 2n plus 1 all over 6. Clean these up a little bit algebraically. Take the limit as n goes to infinity, add them together, and we'll get a sum of 5/3. So 5/3 would represent the area under the curve. Last little thing here, and then we're done. A couple of vocabulary terms here. Inscribed rectangles, if you see that term in the textbook, those are meant to be rectangles that are entirely below the curve. You might see the term circumscribed rectangles. Those would be rectangles that are entirely above the curve. So if you see any problems in the textbook where they mention those terms, that's what they're talking about.